Welcome to this lecture series in real analysis. In this lecture, we'll talk about exponentiation of an arbitrary positive real. We have been exponentiating things since childhood. For example, given any real number x, we can talk about x to the power 1, x to the power 2, x to the power 3, and so on. In fact, we can take negative powers like this. We can also take surds, so we can take fractional powers, things like this, and so on. But so far, we have not discussed any way to make sense of something like this, x to the power root 2. What does that mean? So that is what we are going to cover in this lecture, and we will make use of the exponential and the logarithmic functions to define, or not define really, but make sense of those things. We'll see, and let me just jot down or recall these properties of the logarithmic function. By definition, the logarithmic function or the natural logarithmic function is the inverse of the exponential, and these are two properties that we saw. All right. Some problems for practice. And now let us get started. So as I said in the beginning, how can we make sense of something like this? 3 to the power root 2. Right? And whatever is going to be our definition, it should extend our usual definition of exponentiation. So what we want to do really is, for example, we want to define in particular a function from reals to reals, or reals to positive reals, if you will, which takes a real number x and answers or outputs this number in such a way that it extends our usual exponentiation in a natural way. And it preserves the properties of exponentiation that we enjoy or have been enjoying so far. So for example, we would like to have this property that 3 to the power x plus y is 3 to the power x times 3 to the power y. And 3 to the power x to the power y is 3 to the power x times y. Such properties we want. And of course, we would like to preserve the usual, on natural numbers, this function should behave as the usual exponentiation and so on. So we would like a function like that. And what is the idea? The idea is, first make sense of 3 to the power a rational number. And 3 is not sanctimonious, any positive real to the power a given rational. First, we want to make sense of that. Once, suppose we have defined it, and it is not going to be very hard to define it because we already know how to do surds. This we already know, right? If you have a positive real, you can take any surd you like. So rationals are not very far away. So once you do it for rationals, we will exploit the density of rationals in the reals. So 3 to the power x would then be defined as take any sequence of rational numbers which converges to x, and hope that this thing, whatever we define these things to be, they also converge, this sequence converges. Whatever this converges to will be declared as 3 to the power x. And here there is an obvious issue of well-definedness, because there could be many sequence of rational numbers which converge to a given real number. So we have to get around all those things, but that is the idea. So I'm not going to write that down, but I've said it in words as to what is the roadmap. So now let's define the exponentiation to a rational number. So fix a positive real, a be a positive real, and r be a rational number. Then we define a to the power r as a to the power p to the power 1 by q, where r is equal to p by q. P is an integer and q is a positive integer, natural number. Every rational can be written like this, and a to the power p is our usual a to the power p. P is an integer, so we know how to take a to the power p. A is a positive real, so a to the power p is well defined. Now a to the power p is some other positive real number, and we can take any surd we like. In particular, we can take the qth surd. Even here, there is a well-definedness issue, because a rational number can be expressed as the ratio of two such things, an integer and a natural number, in many ways. But those ways are unique up to scaling by a natural number. So you can scale p by a natural number and scale q by the same natural number. You will get the same rational number as the ratio. And one needs to just check that this remains well defined up to that little bit of non-uniqueness. And that's a simple exercise, so I leave it to you. All right, so we have defined this function which at least takes a rational number and outputs a positive real, a going to a to the power r. Sorry, r going to a to the power r. A is a fixed positive real. So fine. So we just want to extend that to real numbers, and to do that we will first have some preparation. So here is a simple exercise that if x is a real number and r is a rational number, then the exponentiation of x, or the exponential of x to the power r, which we just defined. This is a positive real to the power a rational. So we have defined it. That is equal to this thing. And this I leave as an exercise. It's a very simple exercise. Just use the homomorphism property of the exponential function, etc. Okay. Once we have that with us, we finally have one key lemma. Suppose A is a positive real and Rn is a sequence of rational numbers which is convergent. So fix a convergent sequence of rational numbers. Then we get this sequence, since we defined what is the meaning of a to the power some rational, a to the power any rational is well defined. So we get a new sequence of real numbers, and we claim that this is also convergent. So if you have a convergent sequence of rationals, you get a convergent sequence after you exponentiate. Very simple reason. The proof is as follows. So let a be equal to x of s. Since a is a positive real, it is going to be the exponential of some real number s. S is not positive. S may be negative, but a is positive. So we can do this. And now say, we don't need to say anything. So we have a to the power Rn is x of s to the power Rn, but by the previous lemma, it is equal to x of Rn times s, or let me write s times Rn, and therefore this limit exists. Why does this limit exist? Because x is a continuous function in particular, and this is a convergent sequence. We had Rn as a convergent sequence. If you scale it by s, you still get a convergent sequence, and hence this is a convergent sequence by the continuity of the exponential, and therefore this limit exists. Great, so we have this equality, and that proves this lemma, that this sequence is convergent. And now, for one little bit of upgradation of it, fix a positive real, and suppose we have two sequences of rationals, both of them convergent, and such that they have the same limit. Then we claim that the corresponding exponentiated sequences also have the same limit. The limits of both of them exist by the previous lemma, but here we are claiming that the limits are also the same. So if you take two different sequences of rationals with the same limit, the exponentiated sequences also have the same limit. And the proof of this is just what we wrote here, nothing new. The proof is an exercise, but it has already been done. If you just look at this, this will be clear. So having this thing in hand, we can define the exponential of a for any real number x. So here is the definition. If a is a positive real and x is a real number, then we define a to the power x as the limit where Rn is any sequence of rationals which converges to x or converging to x. This is a proper definition by the previous lemma. Because no matter what sequence of rationals you take which converges to x, this limit will be the same. So this is well defined. Okay. And here is the key theorem that we can express a to the power x in terms of the exponential and the logarithmic function. So a to the power x under this definition is x of x log a. Okay, and note that this generalizes our, by once we prove this theorem, we see that a to the power n, where n is a natural number, is x of n log a, but n log a is log a to the power n, which is equal to a to the power n because exp and log are inverses of each other. So, okay, so what I meant was the following. When I wrote a to the power n, I meant under this definition. By this theorem, this a to the power n is x of n log a, which is equal to x of log a to the power n. And when I wrote a to the power n here, I meant under our usual, familiar way of writing a to the power n. And this now shows that the a to the power n under this definition is same as the a to the power n under our usual definition. Another way to see this is the following. Once we have a natural number here, you can take the constant sequence of rationals n. This is a sequence of rationals which converges to n, and then be done with it. But whatever. So what I'm trying to say is that this definition, once we prove this theorem or otherwise, this definition of a to the power x extends our familiar definition of exponentiation of a to integers. All right, so why is this true? Proof is as follows. Again, let a as exp of s for some real number s, and let Rn be a sequence of rationals which converge to x. Okay, so thus by definition a to the power x is limit a to the power Rn, but this is equal to limit x of s to the power Rn, but as seen in the previous slide, this is x s times Rn, which by continuity of the exponential, the limit can be pushed inside, which is sx. But what is s? We had this equation. So what is s? If you take log on both the sides, we see that s is log a. We could have left it here, but this s is not looking very good. So this is just log a, or I could write it as x times log a. Right, s is log a and this x comes here. We just switched their positions. That's it. It's the same reasoning that we saw in the previous slide. I have repeated it. So we have that. And now finally, using this theorem, we can prove this lemma. If you have a positive real a, two real numbers x and y, then the familiar properties of exponentiation are preserved. So let me just talk about the first one. The second one will be an exercise. So proof of 1. Let me call this 1. This as 2. We have, by the previous theorem, a to the power x plus y is x of x plus y log a, which is x of x log a plus y log a, which is by homomorphism property of the exponential. And this is equal to a to the power x times a to the power y, again by the previous theorem. That's proof of 1, and proof of 2 is again, just use the previous theorem. It's a little trippy, but nothing, not a challenge. Okay, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.